Hey everyone! From the moment humanity first lifted its gaze to the vast inky canvas above, a profound and timeless question was born. What were those countless pinpricks of light? What governed the majestic sweep of the sun across the day, or the moon's mysterious dance through its phases? Before telescopes pierced the veil of distance, before complex equations charted invisible forces, there was only the sky, an endless source of wonder, fear, and an undeniable urge to understand. This is the story of that primal curiosity, a journey through the very earliest attempts to decipher the celestial tapestry, and how the heavens shaped our world long before we ever truly understood them. Before we start, I would like to know where you are watching this video from, and what time is it? Let me know in the comments down below. Also, while you are at it, please do like and subscribe, so we can bring out more content like this. Now let's get started. Imagine, if you will, a group of our distant ancestors huddled around a flickering fire as the twilight deepened. The day's hunt was done, the meager meal shared, as the last embers of the sun dipped below the horizon, painting the western sky in hues of orange and purple. A new world began to unfurl above them. First, the shy emergence of the evening star, then the bold declaration of the moon, a sliver of silver or a full luminous orb, casting long, dancing shadows across the landscape. And finally, as the darkness deepened to an inky velvet, the stars exploded into view, a dazzling countless multitude, each a pinprick of distant light against the infinite black. There was no light pollution then, no electric glow to dim the celestial spectacle. The Milky Way would have stretched across the zenith like a luminous river, a shimmering band of countless stars, inspiring both wonder and perhaps a touch of primal fear at the sheer immensity of it all. The air would have been crisp, the silence profound, broken only by the crackle of the fire and the distant calls of nocturnal creatures. In such an environment, the sky was not merely a backdrop, it was a dominant, ever-present force, a source of light, mystery, and profound significance. What did they see? Not just random points of light. Surely, they saw patterns, subtle shifts, a grand, slow-motion ballet that unfolded night after night, season after season. They saw the familiar arc of stars that seemed to wheel around a fixed point in the northern sky, a celestial anchor in a world of constant change. They noticed how certain bright stars would appear just before dawn at one time of year, only to vanish for months, then reappear again, signaling a new season. They observed the moon waxing and waning, a reliable clock in the sky, marking the passage of shorter cycles. These were not abstract observations, they were intimately tied to the very fabric of their survival. Life for these early peoples was a precarious balance. They lived by the hunt, by the gathering of wild fruits and grains, by the migration of animals. Their very existence depended on knowing when the salmon would run, when the berries would ripen, when the great herds would move across the plains, and the sky, they slowly came to realize, held the key to these vital predictions. The sun, their ultimate life-giver, was the most obvious marker. Its journey across the sky, its rising and setting points shifting subtly with each passing day, dictated the length of daylight, the intensity of warmth, the very cycle of growth and decay. They saw how the sun climbed higher in the summer sky, bringing long, warm days, and sank lower in the winter, ushering in the biting cold and short dark hours. This annual oscillation was not just observed, it was felt in their bones, in the gnawing hunger of winter, in the joyous abundance of summer. The sun's position at noon, the length of the shadows it cast, the very angle of its light filtering through the trees, all these were subtle yet powerful indicators of the passage of time and the approach of critical junctures in the natural world. The moon, too, was a constant companion, its phases a natural calendar, from the slender crescent to the full, radiant disk, and back again. The lunar cycle provided a shorter, more immediate rhythm. Perhaps they used it to plan their hunts, to gather by its light, or simply to mark the passage of time in smaller increments. Imagine a hunter planning a nocturnal ambush, waiting for the full moon to illuminate the landscape, or a gatherer knowing that certain plants were ready for harvest after a specific number of lunar cycles. The moon's phases also influenced tides, which would have been crucial for coastal communities reliant on fishing and shellfish gathering. The ebb and flow of the waters linked directly to the moon's gravitational pull would have been another powerful, observable rhythm. This was practical astronomy, born of necessity, honed by generations of keen observation. But beyond the purely practical, there was something deeper at play. The sky was not just a clock or a calendar, it was a source of profound mystery and awe. The sheer scale of it, the endless expanse, the silent procession of celestial bodies must have filled them with wonder. It was a realm of powerful unseen forces, a place where gods might dwell, where the spirits of ancestors might journey. The stars, unchanging in their patterns yet constantly moving across the night, became familiar faces, perhaps even imbued with personalities or stories. The constellations, those imagined figures drawn between the stars, were likely the earliest attempts to impose order and meaning on the bewildering chaos of the night sky. A hunter might see a great bear in the northern sky, a farmer might see a plough, a warrior might see a hero. These were not just random groupings, they were narratives, mnemonic devices, ways to remember and transmit knowledge across generations, and perhaps ways to connect with the divine. The stories told around the fire at night, under the very stars they described, would have cemented these celestial narratives in the collective consciousness, weaving the fabric of their culture directly into the cosmic tapestry. This fusion of the practical and the spiritual is evident in the earliest surviving testaments to human astronomical ingenuity. The megalithic structures scattered across the globe, these aren't just piles of rocks, they are monumental expressions of a profound understanding of the cosmos, built by societies that possessed no written language, no metal tools, yet commanded an astonishing level of organizational skill and astronomical insight. Consider the vast, enigmatic circles of Stonehenge on the Salisbury Plain in England. For millennia, this iconic monument has stood as a silent sentinel, its massive sarsen and bluestone pillars defying the ravages of time. It wasn't built in a single burst of activity, but evolved over thousands of years, beginning as a simple earthwork enclosure around 3000 BCE and culminating in the complex stone arrangements we see today around 2500 to 1000 BCE. The sheer effort involved is staggering. Stones weighing many tons transported from miles away, shaped and then erected with a precision that still baffles modern engineers. The sarsen stones, some weighing up to 50 tons, were quarried over 20 miles away, while the smaller blue stones, weighing up to 4 tons each, were brought from the Preseli Hills in Wales, a journey of over 150 miles. This feat of engineering, involving thousands of people, immense coordination and generations of labour, speaks volumes about the driving force behind its construction. Why? What drove these ancient people to such monumental feats? The answer, in large part, lies in the sky. Stonehenge is, at its heart, a sophisticated astronomical observatory and calendar. Its most famous alignment points directly to the summer solstice sunrise. On the longest day of the year, the sun rises precisely over the heel stone, its first rays piercing the heart of the monument, illuminating the central altar stone. This wasn't accidental, it was painstakingly engineered. The builders understood the subtle shift of the sun along the horizon throughout the year, and they placed their stones with incredible accuracy to mark this crucial turning point. But the alignments don't stop there. There are also indications of alignments with the winter solstice sunset, where the sun sets precisely between two of the largest sarsen trilithons, casting long shadows into the monument's core. Furthermore, the 4 station stones form a rectangle whose diagonals point to the extreme, rising and setting positions of the moon, suggesting an understanding of the 18.6-year lunar cycle. This wasn't just about marking the solstices, it was about understanding the full sweep of the sun's and moon's journeys across the sky, predicting their movements, and thus predicting the seasons with a precision that would have been invaluable. For a society dependent on agriculture, knowing the precise moment of the summer solstice was crucial. It marked the peak of the growing season, the time when crops were at their fullest, when the days were longest and warmest. It was a time for celebration, for feasting, for giving thanks for the bounty of the earth and the life-giving power of the sun. Similarly, the winter solstice, the shortest day, signalled the turning point, the promise of returning light and warmth, the end of the lean, hungry months. It was a moment of hope, a reaffirmation that the cycle of life would continue, despite the harshness of winter. These were not just dates on a calendar, they were pivotal moments in the annual cycle of life and death, abundance and scarcity. Stonehenge, with its precise alignments, allowed the community to anticipate these moments, to plan their planting and harvesting, to organize their rituals and gatherings. It was a tool for survival, a focal point for communal life, and a sacred space where the earthly and celestial realms intersected, allowing humans to feel connected to the grand cosmic dance. The very act of gathering at Stonehenge for these events would have reinforced community bonds, shared beliefs, and a collective understanding of their place in the universe. Across the Irish Sea in the Boyne Valley of Ireland lies another marvel of prehistoric astronomy, Newgrange. This colossal passage tomb, older than Stonehenge and the Egyptian pyramids, was constructed around 3200 BCE. It is a massive mound of earth and stone, nearly 80 meters in diameter, with a long passage leading to a cruciform chamber at its heart. The mound itself is a feat of engineering, consisting of an estimated 200,000 tons of rock and earth, meticulously piled and capped with a watertight roof. For thousands of years, its secret lay hidden, its true purpose obscured by the passage of time, until its rediscovery in the 17th century, and what a secret it held. Newgrange is meticulously aligned with the winter solstice sunrise. Above the entrance, a specially designed opening known as the roof box allows a narrow beam of sunlight to penetrate the long passage, which is over 19 meters 62 feet long. For a few precious minutes around the winter solstice, as the sun rises, this beam slowly illuminates the inner chamber, culminating in a dramatic illumination of the triple spiral carving on the back wall. This breathtaking event, witnessed by only a handful of people each year, is a testament to the profound astronomical knowledge and spiritual beliefs of its builders. The precision required to construct such an alignment, ensuring that the light would reach the inner chamber only at this specific time of year, is astounding. It speaks of a deep understanding of the sun's annual path, and the ability to translate that understanding into a monumental, enduring structure. Why the winter solstice? For these early farming communities, the winter solstice was a time of deep anxiety. The days were short, food was scarce, and the cold was relentless. The return of the sun, symbolized by its light penetrating the tomb, was a promise of renewal, of life triumphing over death, of the earth awakening once more. It was a powerful symbol of hope and continuity. Newgrange was not just a burial place, it was a monumental calendar, a sacred space for rituals of rebirth, a place where the living could connect with their ancestors and the cosmic cycles that governed their world. It speaks of a society that understood the subtle movements of the sun with astonishing precision and possessed the organizational capacity to translate that understanding into an enduring architectural masterpiece, a beacon of light in the darkest time of the year. The astronomical significance of megalithic structures isn't confined to Western Europe. Across the globe, similar patterns emerge, demonstrating a universal human impulse to connect with the heavens. In Brittany, France, the vast alignments of Karnak, with thousands of standing stones arranged in precise rows, hint at complex astronomical or calendrical functions, though their exact purpose remains debated. Some theories suggest alignments with solstices, equinoxes and lunar cycles, pointing to a sophisticated understanding of celestial movements by the Neolithic peoples who erected them. The sheer scale of Karnak, stretching for kilometers, with some stones weighing hundreds of tons, suggests a massive communal effort, driven by a shared understanding of the importance of the sky, and perhaps a desire to create a landscape-sized calendar or ritual space. The meticulous arrangement of these stones, often in parallel rows, implies a deliberate design, a grand vision that extended far beyond simple marking of territory. Further afield, in the remote Sahara Desert of Egypt, lies Nabta Playa, an even older site that predates Stonehenge and Newgrange by thousands of years. Around 7000 BCE, long before the pharaohs and their pyramids, a nomadic cattle-herding people constructed a stone circle and other megalithic structures here. This calendar circle, as it's known, consists of 4 sets of standing stones, with 2 pairs aligned to the summer solstice sunrise and sunset. Other alignments point to the rising of certain bright stars, like Sirius, which would have been crucial for predicting the arrival of the monsoon rains, vital for their survival in an increasingly arid environment. Nabta Playa demonstrates that the impulse to mark celestial events, to build monumental calendars, was not limited to settled agricultural societies, but emerged even among nomadic groups. driven by the same fundamental needs for timekeeping and prediction. The fact that these early structures were built by a nomadic people highlights how deeply ingrained astronomical observation was, even for those constantly on the move, adapting to changing environments. Their very survival depended on understanding the subtle cues of the heavens that signaled the availability of water and pasture. These structures, whether grand stone circles or humble alignments of natural features, were the culmination of millennia of patient collective observation. How did this knowledge accumulate? It was passed down orally, through stories, songs, and rituals. The elders, the shamans, the wise men and women of the tribe would have been the keepers of this celestial law. They would have taught the younger generations to watch the sky, to recognize the patterns, to understand the subtle cues that signaled the changing seasons. This was a living knowledge, deeply embedded in their culture, essential for their survival. Imagine the scene, a starry night, the flickering firelight illuminating the faces of a rapt audience, as an elder recounts the tale of the great hunter constellation, explaining how its appearance signals the time for the annual deer migration, or how the river of stars, the Milky Way, guides travelers across the vast plains. This oral tradition was the primary means of knowledge transmission, making it both powerful and fragile, dependent on memory and consistent retelling. The tools of these early astronomers were simple, yet effective. Their own eyes were their primary instruments, honed by constant vigilance and a lifetime spent outdoors. The horizon was their baseline, the rising and setting points of the sun and moon their fundamental measurements. A distant peak, a notch in a ridge, a specific tree, these natural landmarks became their sighting posts, allowing them to track the subtle shifts in the sun's and moon's paths over the year. A simple stick cast a shadow, and by marking the length and direction of that shadow at different times of day and year, they could begin to understand the sun's movement. These were the first gnomons, the precursors to sundials, allowing for the tracking of daily and seasonal time. They might have used stretched cords or simple plumb bobs to ensure verticality and level surfaces, fundamental for accurate alignments. The very landscape became their observatory. A cave mouth might frame a particular star at a specific time of year, or a natural rock formation might align with the equinox sunrise. Over time, they began to modify the landscape, adding stones, digging ditches, shaping the earth to enhance these natural alignments, to create more precise and permanent markers. The construction of these megalithic sites was not just about engineering, it was about transforming the earth into a vast open-air clock, a cosmic temple. The stones themselves became extensions of their vision, solidifying ephemeral celestial events into tangible, enduring markers on the landscape. The motivation behind these monumental endeavors was multifaceted. There was the undeniable practical need, knowing when to plant, when to harvest, when to move with the migrating herds. The difference between survival and starvation often hinged on accurate timing. But there was also a profound spiritual dimension. The sky was not just a physical space, it was a sacred realm. The sun was often deified, a source of life and warmth, its daily journey a metaphor for life and death. The moon, with its cyclical rebirth, was associated with fertility, the feminine, and the mysteries of the night. The stars, unchanging and eternal in their patterns, represented the ancestors, the gods, the unchanging order of the cosmos, a source of comfort and guidance in an often unpredictable world. Eclipses, comets, and meteors would have been seen as powerful omens, direct messages from the heavens, often interpreted by shamans or priests who held significant power within the community. The act of observing the sky was therefore not just a scientific endeavor, but a deeply religious one, a way to commune with the divine, to understand their place in the grand cosmic order, and to seek favor from the powerful forces that govern their lives. Rituals and ceremonies would have been intimately tied to these celestial events: dances under the full moon, feasts at the summer solstice, solemn gatherings at the winter solstice to encourage the sun's return and ensure the continuation of life. The people who built these structures were not primitive in their thinking. They were keen observers, logical thinkers, and highly organized individuals. They understood the concept of cycles, of cause and effect, of prediction based on observed patterns. Their knowledge was empirical, built on generations of careful observation and practical application. They didn't have telescopes or complex mathematical equations, but they had patience, persistence, and an intimate connection to the natural world. They lived in a world where the boundary between the natural and the supernatural was fluid, where the movements of the heavens were seen as direct communications from the divine. Their understanding of the world was holistic, integrating the physical, the spiritual, and the social into a unified worldview. The absence of written records from this period means that much of our understanding is based on archaeological evidence and informed speculation. We can measure the alignments of the stones, carbon date the materials, and infer the astronomical knowledge of their builders. But the stories they told, the myths they wove around the constellations, the specific rituals they performed, these are largely lost to us, carried only on the winds of time. Yet, the stones themselves speak volumes. They are silent witnesses to a time when humanity first lifted its gaze from the earth and began to truly see the cosmos, not just as a backdrop to their lives, but as an active participant, a grand celestial clock that governed their very existence. The very act of constructing these enduring monuments suggests a desire to leave a legacy, to transmit this vital knowledge across generations, to ensure the continuity of their culture and their connection to the cosmos. This era, stretching back into the mists of prehistory and slowly giving way to the first written civilizations, was a time of profound discovery. It was the age when humanity first realized that the seemingly chaotic dance of the stars and planets was, in fact, governed by predictable patterns. It was the age when they began to understand that by observing these patterns they could unlock the secrets of time, predict the seasons, and bring a measure of order and predictability to their often unpredictable lives. The megalithic structures, the simple alignments, the oral traditions, these were the first chapters in humanity's grand astronomical story, etched not on parchment or clay, but in the very landscape, in the echoes of stones that still whisper tales of ancient skywatchers to those who pause to listen. The transition from purely nomadic hunter-gatherer societies to more settled agricultural communities around the Neolithic period dramatically increased the need for accurate timekeeping. When people began to cultivate crops, the timing of planting and harvesting became critical. A few weeks' error could mean the difference between a bountiful yield and starvation. The sun's annual cycle, marked by the solstices and equinoxes, became the primary calendar for these agrarian societies. The ability to predict the longest day, the summer solstice, meant knowing when to expect the peak growth of crops, when the sun's energy was at its maximum. The shortest day, the winter solstice, signaled the dormant period, the time for planning and conserving resources, but also the promise of spring's return, a crucial psychological and practical turning point. Beyond the sun, the stars played a crucial role in regulating agricultural cycles. In many parts of the world, the heliacal rising of a particular star, its first appearance in the eastern sky just before dawn, after a period of invisibility, signaled a specific event. For instance, in ancient Egypt, the heliacal rising of Sirius, Sopdet to them, the brightest star in the night sky, coincided almost perfectly with the annual flooding of the Nile River, an event absolutely vital for the fertility of their lands. This celestial event was not just observed, it was celebrated, revered, and used as the cornerstone of their calendar. The knowledge of when Sirius would reappear was passed down through generations, a sacred piece of wisdom that ensured the survival and prosperity of their civilization. Similarly, in other regions, the appearance of specific constellations might have signaled the time for planting certain crops or the arrival of migratory birds or fish. The concept of a year itself was a human construct, an attempt to synchronize human activity with the natural cycles of the heavens. Early calendars were often lunar, based on the easily observable phases of the moon. However, a purely lunar calendar doesn't perfectly align with the solar year and the agricultural seasons. A lunar month is approximately 29.5 days, meaning 12 lunar months total, about 354 days, falling short of the solar year by about 11 days. This discrepancy led to the development of lunar-solar calendars, which attempted to reconcile the two, often by adding intercalary months or days to keep the calendar aligned with the seasons. This was a complex astronomical challenge, requiring careful observation and adjustment, and it was one of the earliest instances of humans grappling with the intricacies of celestial mechanics and the need to create a predictable system out of seemingly disparate cycles. The very act of attempting to reconcile these cycles speaks to a sophisticated level of abstract thought and mathematical understanding, even if unwritten. The very act of building these massive stone structures suggests a level of social organization and shared purpose that is remarkable for the period. It wasn't just a single individual making observations, it was a community, perhaps even multiple communities, collaborating over decades or even centuries. This implies a shared belief system, a common understanding of the importance of the sky, and a collective investment in creating monuments that would serve future generations. The knowledge of how to move and erect such massive stones, how to survey the land and align the structures with precision, was itself a testament to their ingenuity. The leadership required to mobilize hundreds or thousands of people to feed them, house them, and direct their labor towards such a long-term, non-immediate goal speaks to a powerful social structure and a deep cultural commitment to these celestial endeavors. The spiritual dimension of early astronomy cannot be overstated. For these ancient peoples, the cosmos was not a cold, indifferent machine. It was alive, imbued with spirit and power. The sun was a deity, the moon a goddess, the stars were the eyes of ancestors, or the dwelling places of gods. Eclipses, comets, and meteors would have been seen as powerful omens, direct messages from the heavens, often interpreted by shamans or priests who held significant power within the community. The act of observing the sky was therefore not just a scientific endeavor, but a deeply religious one, a way to commune with the divine, to understand their place in the grand cosmic order, and to seek favor from the powerful forces that govern their lives. The alignments of the stones were not just scientific measurements, they were sacred pathways, portals connecting the earthly realm with the celestial, allowing for a tangible connection to the divine. The concept of time itself was deeply intertwined with celestial observations. Before clocks, before written records, time was measured by the sun's passage across the sky, by the length of shadows, by the phases of the moon, and by the annual cycle of the stars. The day began with sunrise and ended with sunset, often marked by specific rituals or activities. The month was marked by the moon's cycle, dictating specific gatherings or hunting patterns. The year was defined by the sun's journey through the constellations, signaling the seasons for planting, harvesting, and migration. This natural rhythm of time was the only rhythm they knew, and it shaped every aspect of their lives, from their daily routines to their seasonal migrations and their sacred ceremonies. It was a time when human life was inextricably linked to the pulse of the universe. The stories and myths woven around the constellations were not mere fanciful tales. They served several crucial functions. Firstly, they were mnemonic devices, helping people remember the patterns of the stars and their associated seasonal significance. By telling stories about Orion the Hunter or Ursa Major the Bear, they could easily identify these star groups and recall when they appeared in the night sky and what that appearance meant for hunting, planting, or navigating. Secondly, these myths provided a framework for understanding their world, connecting the human experience to the vastness of the cosmos. The actions of gods and heroes in the sky mirrored the struggles and triumphs of human life, providing meaning and moral guidance, explaining the inexplicable and offering comfort in the face of the unknown. Thirdly, they fostered a sense of shared cultural identity, a common narrative that bound communities together, reinforcing their collective understanding of the world and their place within it. These celestial narratives were the bedrock of their worldview, passed down with reverence and reinforced through generations. The earliest forms of writing or record-keeping related to astronomy might have been incredibly simple, notches on bones or sticks to count lunar phases, or perhaps markings on cave walls depicting celestial events. These humble beginnings were the precursors to the sophisticated astronomical tables and texts that would emerge in later civilizations. They represent the first attempts to externalize knowledge, to create a permanent record that could be passed down more reliably than oral tradition alone. These early marks, though rudimentary, signify a crucial cognitive leap, the desire to quantify, to record, to formalize observations, moving beyond mere memory to a more systematic approach to understanding the heavens. The development of astronomical knowledge was a slow, iterative process, spanning thousands of years. It wasn't a sudden flash of insight, but a gradual accumulation of observations, refined over countless generations. Each generation built upon the knowledge of the last, adding new observations, correcting old assumptions, and deepening their understanding of the celestial dance. This collective wisdom, passed down through the ages, formed the bedrock upon which all later astronomical advancements would be built. The very concept of progress in this context was measured not in years or decades, but in centuries and millennia, a testament to the patient, persistent curiosity of early humanity. As we move closer to the end of this prehistoric period, we begin to see the emergence of more complex societies, particularly in fertile river valleys like the Nile and the Tigris-Euphrates. These societies, with their settled agricultural practices, larger populations and nascent forms of governance, had an even greater need for precise timekeeping and calendrical systems. The ability to predict the seasons, to organize large-scale labor for irrigation projects, to manage food surpluses, and to coordinate religious festivals became paramount. The foundations laid by the prehistoric skywatchers, with their keen observations and monumental structures, provided the essential knowledge base for these emerging civilizations to take astronomy to the next level, transforming it from a communal, ritualistic practice into a more formalized, specialized discipline. The dawn of astronomy, therefore, was not a single moment, but a long, slow sunrise, stretching across millennia. It began with a simple gaze upwards, a spark of curiosity, a primal need to understand the world. It evolved through countless nights of patient observation, through the construction of monumental testaments to celestial knowledge, and through the weaving of myths and stories that connected humanity to the vast, mysterious cosmos. The echoes of these early skywatchers still resonate in the stones they left behind, whispering tales of a time when the heavens were not just a distant spectacle, but an intimate, living presence, guiding the very pulse of human life. This was the era when humanity first began to read the grand cosmic script, a script written in the language of light and shadow, of cycles and seasons, a language that would continue to challenge and inspire us for millennia to come. The foundations were laid, the stage was set, and the long, winding journey of astronomical discovery had truly begun. The silent, enduring megaliths stand as a testament to this foundational period, reminding us that even without the tools and theories of modern science, our ancestors possessed an incredible capacity for observation, deduction, and a profound connection to the universe above them. As the echoes of the megalithic builders faded into the mists of prehistory, a new chapter in humanity's celestial story began to unfold in the fertile river valleys of the ancient world. Here, where great rivers nourished the land and allowed for settled agriculture, populations swelled, villages grew into towns, and towns into the first true cities. With this burgeoning complexity came new needs for organized governance, for trade, for large-scale construction, and crucially, for more precise and systematic ways of understanding time and the cosmos. The intuitive oral traditions of the Stone Age gave way to the meticulous written records of civilizations that sought to capture the heavens on clay tablets and papyrus scrolls. This was the era when the silent, watchful gaze of our ancestors transformed into a deliberate, calculated study, giving birth to recorded astronomical knowledge. Our journey first takes us to Mesopotamia, the land between the two rivers, the Tigris and the Euphrates. Here, in what is often called the cradle of civilization, the Sumerians laid the groundwork for many of the advancements that would define the ancient world. They were innovators in writing, mathematics, and urban planning, and their fascination with the sky was profound. For the Sumerians, and later the Babylonians and Assyrians who inherited and built upon their legacy, the heavens were not just a source of wonder but a living, breathing entity, a direct conduit to the will of the gods. Every celestial event, from the rising of the sun to the fleeting appearance of a comet, held profound significance, a message to be deciphered, an omen to be interpreted. Imagine the bustling streets of Ur or Babylon, teeming with merchants, artisans, and priests. High above the city, on the towering ziggurats, massive, stepped temple towers, priests and scribes would ascend each night, their eyes fixed on the celestial sphere. These weren't just religious structures, they were also the earliest observatories, elevated platforms designed to provide an unobstructed view of the heavens. From these vantage points, they meticulously tracked the movements of the Sun, Moon, and the 5 visible planets, Mercury, Venus, Mars, Jupiter, and Saturn. They noticed how these wandering stars moved against the backdrop of the seemingly fixed constellations, each following its own unique, intricate path. The Babylonians, in particular, became master observers. For centuries, they compiled vast archives of astronomical data, meticulously etched onto clay tablets using cuneiform script. These were not just casual notes, they were systematic records, detailed observations of planetary positions, lunar eclipses, solar eclipses, and the heliacal risings and settings of important stars. They developed sophisticated methods for measuring angles and time, dividing the day into 24 hours, each hour into 60 minutes, and each minute into 60 seconds, a system that still endures today. This sexagesimal-based 60 system, derived from their mathematical prowess, proved incredibly useful for astronomical calculations. Their motivation was deeply rooted in their religious and political systems. The king's legitimacy, the success of the harvest, the outcome of a battle, all were believed to be influenced by the will of the gods, and the gods communicated their will through celestial phenomena. Thus, astronomy was inextricably linked with astrology. The omen texts, thousands of tablets detailing celestial events and their corresponding earthly consequences, were central to Babylonian society. If Jupiter appeared in a certain constellation, it might foretell prosperity for the king. If a lunar eclipse occurred, it could signal impending disaster, requiring elaborate rituals to avert. This constant need for interpretation fueled their observational diligence and their drive to predict future events. The Babylonians developed incredibly accurate methods for predicting lunar and solar eclipses. They recognized the cyclical nature of these events, particularly the Saros cycle, a period of 18 years, 11 days and 8 hours, after which the Sun, Moon and Earth return to approximately the same relative positions, resulting in a similar eclipse. Their ability to predict these awe-inspiring and often terrifying events gave their priests immense power and prestige. They could warn the king, perform the necessary rituals, and demonstrate their unique connection to the divine. This predictive power, born from centuries of painstaking observation and mathematical analysis, represents a monumental leap from the purely observational astronomy of earlier periods. They also developed sophisticated mathematical models to track the irregular movements of the planets. They didn't have a theoretical understanding of orbits in the modern sense, but they created complex arithmetical schemes, essentially tables of positions and velocities, that allowed them to predict planetary movements with remarkable accuracy. These were empirical models derived directly from their vast observational datasets. They tracked the planets as they moved through the zodiac, the band of constellations through which the sun, moon and planets appear to travel. The concept of the zodiac itself, divided into 12 signs, originated in Mesopotamia, providing a celestial framework for their astrological interpretations. From the bustling cities of Mesopotamia, our story turns to the ancient land of Egypt, a civilization shaped and sustained by the life-giving waters of the Nile. Unlike Mesopotamia, where the celestial landscape was seen as a complex web of omens, Egyptian astronomy was primarily driven by the practical need for an accurate calendar and a profound connection to the cycles of rebirth and eternity. The annual flooding of the Nile River was the single most important event in ancient Egypt. It deposited fertile silt onto the agricultural lands, ensuring the bounty of the harvest. Predicting this flood was a matter of national survival, and the key to this prediction lay in the stars. The Egyptians observed that the heliacal rising of Sirius, the brightest star in the night sky, which they called Sopdet, coincided almost perfectly with the beginning of the Nile's inundation. This was a moment of immense significance, celebrated with great reverence. This observation led to the development of their civil calendar, one of the most accurate calendars of the ancient world. It consisted of 365 days, divided into 3 seasons of 120 days each: inundation, growth and harvest, plus an additional 5 epagamenal days added at the end of the year. While it didn't account for the quarter day extra in the true solar year, leading to a slow drift over centuries, it was remarkably precise for its time and remained largely unchanged for millennia. The stability of their calendar, based on the reliable celestial marker of Sirius, reflected the stability and longevity of their civilization itself. Egyptian astronomical knowledge was deeply intertwined with their religious beliefs and monumental architecture. The pharaohs, seen as divine rulers, were responsible for maintaining Mat. The cosmic order and accurate timekeeping was a part of this sacred duty. Temples and pyramids were often aligned with astronomical precision, not just to mark solstices or equinoxes, but also to specific stars. For example, the Great Pyramid of Giza has shafts that align with certain circumpolar stars, like Thuban, the pole star of that era, and with Orion's belt, reflecting their beliefs about the pharaoh's journey to the afterlife among the eternal stars. The sealing of the tomb of Senmut, a high official during the reign of Hatshepsut, c. 1473 + 1458 BCE, provides a stunning example of Egyptian astronomical charts. It depicts the northern constellations, the decans, groups of stars used for timekeeping at night, and planetary positions. These charts were not merely decorative, they served a practical purpose in timekeeping and a religious one in guiding the deceased through the celestial realms. The decans in particular were crucial for measuring time at night. Each decan would rise above the horizon for approximately 10 days, and by observing which decan was rising at a particular hour, the Egyptians could tell the time, essentially creating a stellar clock. Unlike the Babylonians, the Egyptians did not develop highly sophisticated mathematical astronomy or predictive models for planetary movements. Their focus was more on practical calendrical applications and the integration of celestial cycles into their religious and funerary practices. Their astronomy was less about abstract calculation and more about observation for the purpose of timekeeping, religious ritual, and ensuring the continuity of the cosmic order on Earth. The sun god Ra, the moon god Thoth, and the star goddess Sopdet were central figures in their pantheon, reflecting the profound reverence they held for the celestial bodies that governed their lives. Moving eastward across vast deserts and mountains, we arrive at ancient China, another civilization with a rich and distinct astronomical tradition. Chinese astronomy developed independently from its Mesopotamian and Egyptian counterparts, driven by different cultural imperatives but sharing the common thread of a deep connection between the heavens and earthly affairs. For the Chinese, the emperor was the son of heaven, and his rule was legitimized by the mandate of heaven. Celestial phenomena were seen as direct indicators of heaven's approval or displeasure. Anomalous events, comets, supernovae, eclipses, meteor showers, were not just natural occurrences, they were powerful omens, warnings or blessings from the cosmos that directly impacted the emperor's legitimacy and the stability of the empire. This belief fostered an unparalleled dedication to meticulous astronomical record-keeping. The imperial court maintained a highly organized and specialized corps of astronomers and astrologers. Their primary duty was to observe the sky day and night, record every celestial event, and interpret its significance for the emperor. These records, compiled over thousands of years, are astonishing in their detail and continuity. Chinese astronomers recorded the earliest known observations of sunspots as early as 800 BCE, comets, including Halley's Comet on multiple occasions, and supernovae, exploding stars. Their records of the supernova of 1054 CE, which created the Crab Nebula, are among the most valuable historical astronomical records available, providing crucial data for modern astrophysicists. Chinese astronomers developed sophisticated instruments including armillary spheres, which were complex frameworks of rings used to demonstrate and measure the positions of celestial objects. They also developed water-powered astronomical clocks, demonstrating their advanced understanding of mechanics and timekeeping. Their calendar, like others, was lunar-solar, requiring constant adjustment to align with the agricultural seasons. The precision of the calendar was a matter of imperial prestige. A faulty calendar could be seen as a sign of heaven's displeasure and a threat to the emperor's rule. They divided the celestial sphere into lunar mansions or lodges, 28 irregular segments used to track the moon's position. This system, different from the Babylonian zodiac, reflected their unique approach to mapping the heavens. They also recognized the precession of the equinoxes, the slow wobble of the Earth's axis, long before it was understood in the West, demonstrating a deep understanding of long-term celestial cycles. The Chinese approach to astronomy was largely empirical and observational, driven by the need for accurate omens and calendrical precision. While they developed advanced mathematical techniques, their focus was less on theoretical models of planetary motion like the later Greek systems, and more on precise observation and prediction of celestial events for their practical and political implications. The continuous nature of their astronomical records, spanning millennia, provides an invaluable window into the history of the cosmos and the human effort to understand it. Across these diverse civilizations, Mesopotamia, Egypt, and China, a common thread emerges: the profound shift from simple observation to the birth of recorded knowledge, and, crucially, to the beginnings of prediction. In the prehistoric era, knowledge was ephemeral, passed through generations by word of mouth, vulnerable to loss and distortion. With the advent of writing, astronomical observations could be meticulously documented, compiled, and analyzed over vast stretches of time. This accumulation of data was the bedrock upon which all future astronomical understanding would be built. The ability to record allowed for the identification of cycles that were too long or too subtle to be grasped through individual memory alone. The Saros cycle of eclipses, the 18.6-year lunar cycle, the slow drift of the calendar, these patterns only became apparent through centuries of consistent written observation. This systematic approach transformed astronomy from a purely intuitive practice into a more rigorous empirical science. The drive for prediction was a powerful catalyst. Whether it was predicting the Nile flood, the outcome of a battle, or the next solar eclipse, the ability to foresee celestial events gave immense power and legitimacy to those who possessed this knowledge. It allowed societies to plan, to prepare, and to feel a sense of control over an often unpredictable world. This predictive capacity, however rudimentary by modern standards, marked a fundamental turning point. It moved humanity beyond simply reacting to celestial events to actively anticipating them, a crucial step towards understanding the underlying mechanisms of the universe. This era also saw the professionalization of astronomy. No longer was it solely the domain of tribal elders or shamans. In these complex societies, specialized roles emerged: scribes dedicated to recording celestial data, priests responsible for interpreting omens, and official astronomers tasked with maintaining the calendar and advising the ruler. These individuals formed the intellectual elite, their knowledge highly valued and often shrouded in secrecy. The instruments of this age, while still simple compared to later inventions, represented significant advancements. The gnomon evolved from a simple stick to monumental obelisks in Egypt, casting shadows that marked the hours and seasons. Water clocks and sundials became more sophisticated, allowing for more precise timekeeping throughout the day and night. The Babylonian astrolabe, a precursor to later Greek and Islamic instruments, was used to identify stars and constellations and to measure their positions. These tools, though basic, allowed for increasingly accurate measurements, pushing the boundaries of observational precision. The concept of a fixed celestial sphere with stars eternally positioned upon it became widely accepted across these cultures, forming a stable backdrop against which the wandering stars, planets, moved. While their understanding of the true nature of these celestial bodies was still limited, they were seen as gods, spirits, or lights in the heavens. Their meticulous tracking of their paths laid the empirical foundation for later theoretical models. The limitations of this period were also clear. Without a deep understanding of physics or the true scale of the cosmos, explanations for celestial phenomena often remained rooted in mythology and divine intervention. The Earth was almost universally assumed to be the center of the universe, a stationary platform around which all other celestial bodies revolved. This geocentric view, while intuitively appealing, would eventually lead to increasingly complex and unwieldy models as astronomers struggled to reconcile observations with their Earth-centered assumptions. Yet the achievements of this era were monumental. They established the practice of systematic observation, the importance of accurate record-keeping, and the power of prediction. They developed sophisticated calendrical systems that allowed for the organization of complex societies. They created the first star catalogues, the first attempts to map the heavens with precision. They laid the mathematical groundwork that would be inherited and expanded upon by later civilizations. The rivers of starlight flowing through the minds of these ancient observers illuminated not just the night sky, but also the path for future generations of astronomers. From the clay tablets of Babylon to the temple ceilings of Egypt and the imperial observatories of China, the birth of recorded knowledge transformed humanity's relationship with the cosmos. The heavens were no longer just a source of wonder, they were a vast, intricate puzzle, waiting to be solved, piece by meticulous piece. This was the era when humanity truly began to write its own story in the stars, a story of observation, calculation, and the enduring quest to understand the universe. The stage was now set for the philosophical inquiries and mathematical models that would define the next great leap in astronomical thought. As the meticulous record-keeping and empirical predictions of the ancient Near East reached their zenith, a new intellectual current began to stir across the Mediterranean, in the vibrant city-states of ancient Greece. Here, the focus shifted from purely practical applications and omens to a deeper, more philosophical inquiry into the nature of the cosmos itself. The Greeks, inheritors of much of the Babylonian and Egyptian astronomical knowledge, were not content merely to observe and predict. They sought to understand why the heavens moved as they did, to uncover the underlying principles of order and harmony that governed the celestial dance. This intellectual revolution, blending observation with abstract reasoning and mathematical elegance, would shape Western astronomical thought for nearly 2 millennia. Imagine the bustling agora of Athens, philosophers debating under the warm Mediterranean sun, mathematicians meticulously drawing diagrams, and thinkers wrestling with fundamental questions about the universe. The Greeks were driven by a profound desire for logos, for rational explanation, for a cosmic order that could be understood through human reason. They believed that the universe, being a creation of divine intelligence, must be inherently beautiful, harmonious, and geometrically perfect. This aesthetic and philosophical bias would profoundly influence their astronomical models, leading them to prioritize elegant, symmetrical explanations, even when they strained against observational evidence. The earliest Greek thinkers, often called the pre-Socratics, began to move away from purely mythological explanations of the cosmos. Thales of Miletus, considered the first philosopher, is credited with predicting a solar eclipse. Though the accuracy of this prediction is debated, the very idea of it marks a shift. More importantly, he proposed that water was the fundamental substance of the universe, a natural rather than supernatural explanation. Anaximander, his student, conceived of the Earth as a cylinder suspended in space, surrounded by rings of fire that appeared as the sun, moon, and stars. While these early ideas seem quaint to us now, they represented a radical departure, an attempt to explain the world through natural principles, rather than solely through the whims of gods. The Pythagoreans, a mystical and mathematical brotherhood, introduced the profound idea that the universe could be understood through numbers and musical harmony. They believed that the celestial bodies moved in perfect circles, producing a music of the spheres, an inaudible cosmic symphony. This concept of perfect circular motion would become a cornerstone of Greek astronomy, deeply ingrained in their philosophical and aesthetic sensibilities. For them, the circle was the most perfect geometric shape, and therefore the only fitting path for divine celestial bodies. This belief, while elegant, would prove to be a significant obstacle to understanding the true nature of planetary orbits. They were also among the first to propose that the Earth itself was a sphere, a concept supported by observations like the curved shadow the Earth casts on the Moon during a lunar eclipse, and the way ships gradually disappear hull first over the horizon. Plato, one of the most influential Greek philosophers, further solidified the idea of perfect, uniform circular motion as the ideal for celestial bodies. In his dialogue Timaeus, he describes a divine craftsman, the demiurge, who fashioned the cosmos according to mathematical principles, creating a perfectly ordered and rational universe. For Plato, the observable, imperfect world was merely a shadow of a perfect, ideal realm of forms. This philosophical framework meant that astronomical observations, which often showed irregularities in planetary motion, had to be saved by complex mathematical constructions that preserved the ideal of circularity. The challenge posed to astronomers was to save the phenomena, to devise geometric models that could account for the observed movements of the planets while adhering to the principle of uniform circular motion. This challenge was taken up by Eudoxus of Cnidus, 290 to 337 BCE, a student of Plato and one of the most brilliant mathematicians and astronomers of his time. Eudoxus devised the first sophisticated geometric model of the cosmos, a system of concentric crystalline spheres. He proposed that each celestial body, the sun, moon, and each of the 5 visible planets, was embedded in its own set of interconnected transparent spheres, each rotating on a different axis and at a different speed. For example, to explain the seemingly erratic motion of a planet, he might use 3 or 4 spheres nested within each other, their combined rotations producing the observed path. This was an ingenious mathematical construction, an attempt to explain complex observed motions using only perfect circles. Eudoxus's model was a triumph of geometric ingenuity, but it had limitations. It could explain the general motion of the planets, including their retrograde backward loops, but it couldn't account for variations in their brightness, which implied changes in their distance from Earth, nor could it perfectly reproduce the precise paths observed over long periods. Despite its flaws, it established the paradigm of a geocentric, Earth-centered universe composed of nested spheres, a model that would dominate Western thought for centuries. Aristotle, 384–322 BCE, Plato's most famous student, adopted and expanded upon Eudoxus's model, giving it a physical reality. For Aristotle, the universe was a series of 55 concentric crystalline spheres, each carrying a celestial body, all rotating around a stationary Earth at the center. Beyond the outermost sphere, which carried the fixed stars, lay the prime mover, the divine intelligence that imparted motion to the entire cosmos. Aristotle's cosmology was deeply influential, integrating his physics, metaphysics, and astronomy into a coherent, seemingly logical system. He argued for a fundamental distinction between the terrestrial realm, the Earth, which was imperfect, changeable, and composed of the four elements earth, water, air, fire, and the celestial realm, everything beyond the moon, which was perfect, unchanging, and composed of a fifth element, the aether or quintessence. Celestial bodies, being perfect, could only move in perfect circles. The Earth, being heavy and imperfect, naturally rested at the center. This Aristotelian view, with its stationary central Earth and its perfect, unchanging heavens, became the dominant worldview in the West, deeply intertwined with philosophical and theological thought. However, even with Aristotle's refinements, the problem of retrograde motion persisted, and the observed variations in planetary brightness remained unexplained. As observations became more precise, the simple concentric spheres proved inadequate. This led to the development of more complex geometric devices to save the phenomena, while clinging to the geocentric ideal. The solution came with the introduction of epicycles and deferents. This ingenious system was first developed by Apollonius of Perga, c. 262–100 BCE, and Hipparchus of Nicaea, two of the most significant astronomers of the Hellenistic period. Hipparchus in particular was a meticulous observer and a brilliant mathematician. He compiled the first comprehensive star catalogue in the West, listing the positions and brightness of over 850 stars. By comparing his observations with earlier Babylonian records, he discovered the precession of the equinoxes, the slow wobble of the Earth's axis that causes the apparent position of the celestial pole and the equinoxes to shift over millennia. This was a monumental discovery, revealing a long-term celestial cycle that had previously gone unnoticed in the West. Hipparchus refined the epicycle deferent model. In this system, a planet P does not orbit directly around the Earth. Instead, it moves in a small circle called an epicycle, and the center of that epicycle C moves in a larger circle called a deferent around the Earth. By adjusting the sizes and speeds of these circles, astronomers could explain the retrograde motion of the planets when the planet on its epicycle moves backward relative to the deferent, and also account for variations in their brightness when the planet is closer to Earth on its epicycle. This model, though geometrically complex, allowed for a much more accurate representation of planetary paths than Eudoxus concentric spheres. To further refine the model and account for observed irregularities, additional concepts were introduced, the eccentric and the equant. An eccentric model placed the Earth slightly off-center from the deferent, allowing for variations in a planet's speed as it moved around the Earth. The equant, a more controversial device, was a point from which the center of the epicycle appeared to move at a uniform angular speed, even though its actual speed around the deferent was not uniform. While mathematically effective, the equant violated the pure principle of uniform circular motion, a philosophical ideal that the Greeks held dear. It was a pragmatic solution to observational challenges, but one that introduced a degree of intellectual discomfort. The culmination of Greek astronomical thought, and indeed the entire geocentric tradition, came with Claudius Ptolemy, c. 100–170 CE, who lived and worked in Alexandria, Egypt, then a major center of Hellenistic learning. Ptolemy was a polymath, a mathematician, astronomer, geographer, and astrologer. His monumental work, the Syntaxis Mathematica, known to us by its Arabic title, Almagest, the Greatest Treatise, was a comprehensive compilation of Greek astronomical knowledge, refined and expanded by his own observations and mathematical models. The Almagest was a masterpiece of scientific synthesis. In 13 books, Ptolemy presented a fully developed geocentric model of the universe, incorporating all the devices developed by his predecessors, deferts, epicycles, eccentrics, and equants, into a coherent, mathematically rigorous system. He described the Earth as a stationary sphere at the center of the universe, surrounded by the spheres of the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally, the sphere of the fixed stars. Beyond the stars lay the prime mover. Ptolemy's model was incredibly complex, a testament to the ingenuity required to force the observed motions of the planets into an Earth-centered circular framework. For the Moon and Sun, he used simpler eccentric models. For the planets, he combined epicycles and defiants, often with the defiant's center offset from the Earth, eccentric and the epicycle's center moving uniformly with respect to an equant point. The result was a system that, for its time, was remarkably accurate in predicting the positions of the planets. It could explain retrograde motion, variations in brightness, and the general paths of the celestial bodies with impressive precision. The Almagest was more than just a description of a model. It was a practical handbook for astronomers. It contained detailed tables for calculating the positions of the Sun, Moon, and planets for any given time, as well as methods for predicting eclipses. It included a star catalogue building upon Hipparchus's work, listing over 1,000 stars with their coordinates. For centuries, it served as the definitive astronomical textbook, the ultimate authority on the structure and workings of the cosmos. Its influence was immense and enduring, shaping astronomical thought in the Islamic world, and later in medieval Europe. Ptolemy's work was a triumph of the save the phenomena approach. He wasn't necessarily concerned with the physical reality of his epicycles and deferents. Rather, he sought a mathematical model that could accurately predict observations. The elegance and predictive power of the Ptolemaic system was so compelling that it remained largely unchallenged for over 1,400 years. It provided a coherent, albeit complex, explanation for the heavens that aligned with philosophical ideals, perfect circles, central Earth, and religious doctrines, Earth as the focus of creation. However, despite its sophistication, the Ptolemaic system was not without its problems. As centuries passed and new, more precise observations were made, the model required increasingly complex adjustments. New epicycles had to be added to epicycles, and new eccentrics introduced, making the system increasingly unwieldy and less elegant than the Greek philosophers would have preferred. The equant, in particular, was a source of philosophical discomfort, as it violated the principle of uniform angular motion around the center of the circle. Critics would later refer to it as a monstrosity that undermined the aesthetic purity of the Greek ideal. The Greek contribution to astronomy was not just about the geocentric model, it was about the introduction of rigorous mathematical reasoning, geometric modeling, and philosophical inquiry into the study of the heavens. They transformed astronomy from a purely observational and divinatory practice into a theoretical science, seeking to understand the underlying principles of the universe. They asked fundamental questions about the shape of the Earth, its place in the cosmos, and the nature of celestial motion. Eratosthenes of Cyrene, c. 2076-195 BCE, a contemporary of Hipparchus, famously calculated the circumference of the Earth with remarkable accuracy, using simple geometry and observations of shadows cast by the Sun at different locations. By measuring the angle of the Sun's rays at noon on the summer solstice in Sion, modern Aswan, and Alexandria, and knowing the distance between the two cities, he deduced the Earth's circumference to be approximately 250,000 stadia, which is remarkably close to the actual value. This was a stunning demonstration of the power of mathematical reasoning applied to astronomical observations. Aristarchus of Samos, c. 3110-2030 BCE, even proposed a heliocentric sun-centered model of the universe, arguing that the Earth and other planets revolved around the Sun. He also attempted to measure the relative sizes and distances of the Sun and Moon. His ideas, however, were largely rejected by his contemporaries, who found the idea of a moving Earth counterintuitive and inconsistent with Aristotelian physics. The lack of observable stellar parallax, the apparent shift in a star's position due to the Earth's orbit around the Sun, also argued against a moving Earth. If the Earth moved, the stars should appear to shift, and since no such shift was observed, the Earth must be stationary. The stars were simply too far away for parallax to be detectable with the naked eye, a fact unknown to the Greeks. Thus, the geocentric model, reinforced by philosophical and observational arguments, remained dominant. The legacy of Greek astronomy was profound. It established the intellectual framework for understanding the cosmos in the Western world for over a millennium. The emphasis on geometric models, mathematical precision, and the search for underlying harmony would inspire future generations of astronomers. The Almagest became the authoritative text, a beacon of astronomical knowledge that would be preserved, studied, and refined by scholars in other civilizations during Europe's intellectual slumber. The Greeks, through their unique blend of philosophy, mathematics, and observation, transformed astronomy into a true intellectual discipline. They sought not just to know what happened in the sky, but how and why. Their quest for reason and harmony in the cosmos led them to construct an intricate and beautiful, albeit ultimately flawed, model of the universe. This model, with its central Earth and its elegant if complex celestial machinery, represented the zenith of ancient astronomical thought, a testament to the power of human intellect to impose order and understanding on the vastness of the heavens. The stage was now set for the next great act in the cosmic drama, the preservation and refinement of this knowledge in distant lands, and the slow, inexorable accumulation of discrepancies that would eventually lead to a revolutionary shift in humanity's understanding of its place in the universe. As the Roman Empire waned and Europe entered a period often referred to as the Dark Ages, the intellectual flame of classical learning, particularly in astronomy, did not extinguish. Instead, it found a new and vibrant home far to the east in the burgeoning Islamic world. From the 8th century onwards, a remarkable intellectual movement, often called the Islamic Golden Age, swept across vast swathes of the globe, from Spain to Central Asia. Driven by a thirst for knowledge, a reverence for scholarship, and practical needs, Islamic scholars meticulously preserved, translated, and crucially built upon the astronomical heritage of the Greeks, Indians, and Persians. This era was a vital bridge, connecting the ancient world's wisdom with the scientific revolution that would later blossom in Europe. Imagine the bustling libraries of Baghdad, the grand observatories of Moraga and Samarkand, and the vibrant intellectual centers of Cordoba and Cairo. Here, scholars from diverse backgrounds, speaking different languages, united by a common pursuit of knowledge, engaged in a monumental effort of translation. Greek texts, including Ptolemy's Almagest, which had been largely lost or forgotten in the Latin West, were translated into Arabic. This was not a passive act of copying, it was an active engagement, with scholars often correcting errors in the original texts and adding their own commentaries. This commitment to preserving and understanding ancient knowledge was foundational to their own advancements. The motivations for astronomical study in the Islamic world were multifaceted. There was a strong practical imperative. Islam, as a global religion, required precise timekeeping for daily prayers, which had to be performed at specific times of day, determined by the sun's position, and for determining the direction of the Kaaba in Mecca, the Qibla, from any location on Earth. The lunar calendar, central to Islamic religious festivals like Ramadan and the Hajj, also necessitated accurate observation of the moon. These practical needs spurred significant advancements in observational astronomy and mathematical methods. Beyond the practical, there was a deep theological and philosophical motivation. The Quran encouraged the contemplation of the heavens as signs of God's creation and wisdom. Islamic scholars saw no conflict between faith and reason. Indeed, they believed that by studying the intricate workings of the cosmos, they were gaining a deeper understanding of God's design. This intellectual curiosity, coupled with the patronage of powerful caliphs and sultans, led to the establishment of the first true institutional observatories. These observatories were far more than just elevated platforms. They were sophisticated research institutions, equipped with an array of advanced instruments and staffed by teams of astronomers, mathematicians, and instrument makers. One of the earliest and most influential was the House of Wisdom in Baghdad, founded in the 9th century, which served as a center for translation and original research. Later, in the 13th century, the Moraga Observatory in Persia, established by Nasir al-Din al-Tusi, became a leading center of astronomical research. It housed a vast library, a workshop for constructing instruments, and living quarters for scholars. Even more impressive was the Ulugh Beg Observatory in Samarkand, built in the 15th century, which featured a massive Fakhri sextant, an instrument capable of measuring celestial altitudes with unprecedented precision. The instruments developed and refined by Islamic astronomers were crucial to their observational accuracy. The astrolabe, inherited from the Greeks but vastly improved, became a versatile tool for identifying stars, measuring altitudes, determining time, and even solving complex astrological problems. They developed larger and more precise quadrants and sextants, often fixed to the ground, allowing for highly accurate measurements of celestial positions. Sundials became more sophisticated, and water clocks were refined for precise timekeeping. These instruments were not just tools, they were works of art, often beautifully crafted and engraved, reflecting the high esteem in which astronomy was held. Islamic astronomers were not content to simply accept the Greek models without question. They were critical thinkers who rigorously tested the Ptolemaic system against their own observations. While they largely adhered to the geocentric framework, they identified numerous inconsistencies and inaccuracies in Ptolemy's Almagest. They noticed that Ptolemy's models, particularly the equant, violated the Greek philosophical ideal of uniform circular motion around a fixed center. This intellectual discomfort spurred them to seek alternative, more elegant solutions that still preserved the geocentric principle. One of the most significant figures in this critical tradition was Ibn al-Haytham al-Hazen, c. 965–1040 CE, a brilliant polymath from Basra. Though primarily known for his groundbreaking work in optics, he was also a sharp critic of Ptolemy's planetary models. He argued that Ptolemy's equant, while mathematically effective, was physically implausible, as it implied a non-uniform motion that contradicted the philosophical ideal. He sought to replace it with geometrically equivalent models that maintained uniform circular motion. His critiques laid the groundwork for later astronomers to challenge the very foundations of the Ptolemaic system. Other prominent astronomers, such as Ibn al-Shatir, c. 1304–1375 CE, from Damascus, developed sophisticated planetary models that eliminated the equant entirely. Ibn al-Shatir's models, based on a series of epicycles and deferents, were geometrically equivalent to Ptolemy's, but achieved the same predictive power without violating the principle of uniform circular motion. Remarkably, some of his models bear striking similarities to those later developed by Copernicus, suggesting a possible, though debated, transmission of ideas. Beyond refining Ptolemy, Islamic astronomers made numerous original contributions. They compiled new and greatly improved star catalogues, correcting errors in Ptolemy's and adding new stars. For example, Al-Sufi to 909–86 CE produced his Book of Fixed Stars, which included detailed descriptions and illustrations of constellations and was a standard reference for centuries. They also developed advanced mathematical techniques, including trigonometry, which was essential for complex astronomical calculations. The sine, cosine, and tangent functions, fundamental to modern trigonometry, were extensively developed and applied by Islamic mathematicians. They also refined and standardized the methods for calculating the Qibla, direction of Mecca, from any point on Earth, a complex problem involving spherical trigonometry. This practical need led to significant advancements in geography and cartography, as astronomers and geographers worked together to map the world with greater accuracy. The concept of the zero and the Hindu-Arabic numeral system, transmitted to the Islamic world from India and then introduced to Europe, revolutionized mathematical calculation, making complex astronomical computations far easier. This seemingly simple innovation had a profound impact on the efficiency and accuracy of astronomical work. Perhaps one of the most enduring legacies of Islamic astronomy was the establishment of the scientific method, emphasizing empirical observation, experimentation, and rigorous mathematical analysis. While they did not fully break from the geocentric paradigm, their critical approach to existing theories, their dedication to precise observation, and their systematic recording of data laid essential groundwork for the scientific revolution that would follow in Europe. They demonstrated that scientific knowledge was cumulative, built upon the work of predecessors, but also subject to critical scrutiny and improvement. The transmission of this vast body of knowledge to Europe was a slow but ultimately transformative process. During the early Middle Ages, much of the Greek scientific heritage was lost in Western Europe, surviving primarily in fragmented texts and simplified summaries. However, from the 11th century onwards, centers of translation emerged, particularly in Spain, like Toledo and Sicily, where Christian, Jewish, and Muslim scholars collaborated to translate Arabic texts into Latin. The Almagest, along with numerous other Arabic astronomical treatises, mathematical works, and philosophical texts, poured into Europe. This influx of knowledge had a profound impact, reintroducing Europeans to the full scope of Greek science, and crucially, introducing them to the advancements and critiques made by Islamic scholars. Scholars like Gerard of Cremona, so 1014,087 CE, in Toledo were instrumental in translating hundreds of Arabic texts, including the Almagest, making them accessible to Latin-speaking scholars. This rediscovery of classical and Islamic astronomical knowledge sparked a revival of learning in Europe. Universities began to emerge, and astronomy became a central part of the quadrivium: arithmetic, geometry, music, and astronomy, the higher division of the liberal arts. Scholars in medieval Europe began to study Ptolemy's work with renewed vigour, grappling with its complexities and attempting to reconcile it with Christian theology. However, the very sophistication of the Ptolemaic system, as inherited from the Islamic world, also contained the seeds of its eventual demise. The Islamic astronomers had already highlighted its mathematical inconsistencies and philosophical discomforts, particularly the equant. As European scholars continued to observe the heavens with increasing precision, these discrepancies became more apparent. The system, while still predictive, was becoming increasingly unwieldy, requiring more and more epicycles and adjustments to match observations. This growing complexity, a sign that the model was perhaps fundamentally flawed, would eventually lead to a profound intellectual crisis. The Islamic Golden Age of astronomy was a period of immense intellectual vitality and innovation. It was a time when the torch of knowledge, passed from the ancient Greeks, was not only kept alight, but intensified and refined. Islamic scholars were not mere custodians, they were active participants in the scientific process, driven by both practical and spiritual imperatives. Their meticulous observations, their development of advanced instruments, their critical analysis of existing theories, and their groundbreaking contributions to mathematics laid the essential groundwork for the scientific revolution that would follow. Without the efforts of Islamic astronomers, much of the classical heritage would have been lost, and the path to modern astronomy would have been far longer and more arduous. They bridged worlds, connecting the ancient past with the burgeoning future, ensuring that the rivers of starlight continued to flow, nourishing the human quest to understand the vast, intricate tapestry of the cosmos. Their legacy is etched not only in the stars they observed, but in the very methods and instruments that would eventually lead to a revolutionary new understanding of humanity's place in the universe. The stage was now set for the challenges to the geocentric model that would redefine astronomy forever. As the intellectual currents of the Islamic Golden Age slowly but surely flowed back into Europe, primarily through the translation centres of Spain and Sicily, the continent began to awaken from its long intellectual slumber. The period from roughly the 14th to the 16th centuries, known as the Renaissance, was a time of immense cultural, artistic, and scientific rebirth. It was an era marked by a renewed interest in classical antiquity, a spirit of humanism, and a burgeoning curiosity about the natural world. This reawakening provided the fertile ground in which the seeds of a profound astronomical revolution would finally take root. Imagine Europe in the late Middle Ages, a world still largely governed by the philosophical and cosmological framework established by Aristotle and refined by Ptolemy. The Earth was firmly at the centre of the universe, a stationary, unmoving sphere, the unique stage for God's creation and humanity's drama. Around it, the sun, moon, planets and stars revolved in perfect, unchanging circles, embedded in crystalline spheres. This geocentric model, so elegantly described in Ptolemy's Almagest, had been the undisputed authority for over 14 centuries. It was a system that not only aligned with common sense, after all we don't feel the Earth moving, but also dovetailed perfectly with prevailing theological interpretations, placing humanity at the physical and spiritual centre of the cosmos. The rediscovery of classical Greek texts, often through their Arabic translations, was a pivotal moment. Scholars across Europe eagerly devoured works like Ptolemy's Almagest, Euclid's Elements, and the writings of Aristotle. Universities which had begun to emerge in the 12th and 13th centuries became centres for the study of these texts. Astronomy, as part of the quadrivium, was a core subject, taught using Ptolemy's models. Students learned to calculate planetary positions, predict eclipses, and understand the intricate dance of the heavens according to the established geocentric paradigm. The intellectual energy was immense, but initially it was largely focused on understanding and mastering the existing knowledge rather than fundamentally challenging it. However, as the centuries progressed, and as observational techniques slowly improved, a subtle but growing unease began to creep into the astronomical community. The Ptolemaic system, for all its predictive power, was becoming increasingly unwieldy. To account for the observed irregularities in planetary motion, particularly the perplexing retrograde loops where planets appeared to move backward against the background stars, Ptolemy had introduced ingenious but complex mathematical devices: epicycles, deferents, eccentrics, and equants. An epicycle was a small circle on which a planet moved, while the centre of that epicycle itself moved along a larger circle called a deferent, which was centred near the Earth. This allowed for the planet to appear to loop backward. To explain variations in planetary speed and brightness, the Earth was often placed slightly off-centre from the deferent, an eccentric, and the equant was introduced, a point from which the centre of the epicycle appeared to move at a uniform angular speed, even though its actual speed around the deferent was not uniform. The problem was that as astronomers made more precise observations, they found that these models, while good, weren't perfect. To make the predictions match the observations, they had to add more and more layers of complexity. Epicycles were added to epicycles, and new eccentrics and equants were introduced. The system became a tangled web of circles upon circles, a mathematical Frankenstein's monster that, while still functional, had lost the elegant simplicity and harmonious perfection that the original Greek philosophers had so cherished. It was like trying to fix a fundamentally flawed machine by adding more and more gears and levers, each adjustment creating new complications elsewhere. This growing complexity was not just a mathematical inconvenience, it was a philosophical discomfort. The Greek ideal of uniform circular motion, a reflection of divine perfection, was being violated, particularly by the equant. Many astronomers and philosophers felt that the universe, being a creation of God, should be inherently simple and beautiful, not a convoluted mess of mathematical contrivances. The feeling grew that there must be a simpler, more elegant explanation for the celestial movements, one that preserved the aesthetic and philosophical ideals that the Ptolemaic system was increasingly sacrificing for observational accuracy. Beyond these internal intellectual tensions, powerful external forces were also at play, particularly the age of exploration. Beginning in the late 15th century, European navigators embarked on daring voyages across vast oceans, pushing the boundaries of the known world. Christopher Columbus's journey across the Atlantic, Vasco da Gama's circumnavigation of Africa, and Ferdinand Magellan's circumnavigation of the globe transformed global trade and geopolitics. But these voyages demanded unprecedented accuracy in navigation. Sailors needed to know their latitude, and, even more critically, their longitude. While latitude could be determined by observing the height of the sun at noon or the pole star at night, longitude was a far more challenging problem. It required precise timekeeping and accurate astronomical tables to determine the difference in time between the ship's current location and a known meridian. The existing astronomical tables, based on the cumbersome Ptolemy system, were often inaccurate and difficult to use at sea. This practical demand for better navigation provided a powerful incentive for astronomical reform. Merchants, monarchs, and navigators alike clamoured for more reliable methods to guide their ships across the vast, uncharted oceans. The heavens, once primarily a source of divine omens or philosophical contemplation, now became a crucial tool for global commerce and imperial expansion. It was into this intellectual and practical milieu that Nicolaus Copernicus, 1473 to 1543, emerged. Born in Toruń, Poland, Copernicus was a true Renaissance man, a mathematician, astronomer, physician, classical scholar, governor, diplomat, and canon in the Catholic Church. He studied at universities across Europe, including Krakow, Bologna, and Padua, immersing himself in classical learning, mathematics, and of course astronomy. He was deeply familiar with Ptolemy's Almagest and the critiques that had been levelled against it by Islamic astronomers. Like many of his contemporaries, he was troubled by the increasing complexity and lack of elegance in the geocentric model. Copernicus was not a revolutionary in the sense of seeking to overthrow established order. Rather, he was a conservative thinker, driven by a desire to restore the mathematical and philosophical elegance that he felt the Ptolemaic system had lost. He believed that the universe, being a divine creation, must be harmonious and simple. He began to explore alternative models, drawing inspiration from ancient Greek thinkers like Aristarchus of Samos, who had proposed a heliocentric universe centuries earlier, though his ideas had been largely forgotten or dismissed. Copernicus's audacious idea was deceptively simple. What if the Sun, not the Earth, was at the center of the universe? What if the Earth was just another planet, orbiting the Sun, and also rotating on its own axis? This seemingly minor shift in perspective had profound implications. In his seminal work De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, published in the year of his death, 1543, Copernicus laid out his heliocentric model. In his model, the Sun occupied the central position, stationary and unmoving. Around it revolved the 6 known planets in order: Mercury, Venus, Earth with its moon, Mars, Jupiter, and Saturn. Beyond Saturn lay the sphere of the fixed stars, which Copernicus argued were immensely distant, far more so than previously imagined. The Earth itself had 2 motions. It rotated on its axis once every 24 hours, accounting for the apparent daily motion of the Sun and stars, and it revolved around the Sun once a year, accounting for the annual cycle of the seasons and the Sun's apparent movement through the zodiac. The most elegant aspect of Copernicus's model was its ability to explain the perplexing problem of retrograde motion. In the Ptolemaic system, retrograde motion required complex epicycles. In the Copernican system, it became a natural consequence of the Earth's own motion. Imagine 2 cars on a racetrack, travelling in the same direction but at different speeds. When the faster car Earth overtakes the slower car, an outer planet like Mars, the slower car appears, for a brief period, to move backward relative to the background. Similarly, an inner planet like Venus, moving faster than Earth, would appear to oscillate back and forth. This simple, elegant explanation for retrograde motion was a powerful argument in favour of the heliocentric model, restoring a sense of order and simplicity to the planetary dance. Copernicus's model also provided a natural explanation for the varying brightness of the planets. In the geocentric system, it was difficult to explain why Mars, for instance, appeared significantly brighter at some times than others. In the heliocentric model, this was easily accounted for. When Earth and Mars were on the same side of the Sun, Mars was closer to Earth and thus appeared brighter. When they were on opposite sides, Mars was farther away and appeared dimmer. The order of the planets and their orbital periods also fell into a more logical arrangement, with planets farther from the Sun having longer orbital periods, a relationship that would later be formalized by Kepler. Despite its elegance and simplicity, Copernicus's heliocentric model faced immense challenges and resistance. The most immediate and significant problem was the lack of observable stellar parallax. If the Earth truly revolved around the Sun, then the apparent positions of nearby stars should shift slightly against the background of more distant stars over the course of a year, forming a tiny ellipse. Ancient Greek astronomers had looked for this parallax and, finding none, used its absence as a strong argument against a moving Earth. Copernicus's only defense was to propose that the stars were so incredibly distant that their parallax was too small to be detected with the naked eye. This was a correct intuition, but one that could not be proven until the invention of the telescope and more precise instruments centuries later. The sheer scale of the universe implied by Copernicus's model was almost unfathomable to his contemporaries. Another major challenge came from Aristotelian physics, which was the dominant scientific framework of the time. Aristotle's physics dictated that heavy objects naturally moved towards the center of the universe, which was believed to be the Earth. If the Earth were moving, why didn't objects thrown into the air fly off into space? Why didn't we feel a constant wind or centrifugal force? Why did objects fall straight down? These were powerful intuitive and physical arguments against a moving Earth, and Copernicus offered no new physics to explain them. His model was a kinematic description of motion, not a dynamic one. The necessary new physics would only come much later with Galileo and Newton. Furthermore, the heliocentric model clashed with prevailing religious interpretations. The Bible, particularly in certain psalms and passages, seemed to imply a stationary Earth and a moving Sun, while Copernicus himself was a canon in the Church and did not see his work as a direct contradiction of Scripture. The idea of a non-central Earth was deeply unsettling to many theologians. It challenged humanity's perceived unique status in the cosmos and the literal interpretation of sacred texts. The Church, which had largely tolerated Ptolemaic astronomy, viewed Copernicus's ideas with suspicion, especially as the Protestant Reformation was simultaneously challenging its authority. Copernicus was acutely aware of the controversial nature of his ideas. He worked on De Revolutionibus for decades, refining his arguments and calculations, but he hesitated to publish. It was only through the encouragement of a younger scholar, George Joachim Rheticus, that the work finally went to press. Even then, an unauthorized preface was added by the Lutheran theologian Andreas Osiander, presenting the heliocentric model as merely a mathematical hypothesis, a convenient way to calculate planetary positions rather than a physical reality. This preface, intended to soften the blow and avoid controversy, likely contributed to the book's initial reception as a mathematical tool rather than a cosmological truth. Indeed, De Theorie Velocupas was not an immediate sensation. It was a dense, highly technical mathematical treatise, accessible only to a small number of astronomers. Its initial impact was limited, primarily serving as a reference for calendrical reform and further astronomical calculations. For many years, it was viewed as a clever mathematical device, a hypothetical alternative to Ptolemy, rather than a description of the actual universe. It didn't immediately overturn the geocentric worldview. However, the publication of De Revolutionibus marked a profound turning point. It was the first serious, mathematically rigorous challenge to the geocentric paradigm in over a millennium. It provided an alternative framework, a new way of conceptualizing the cosmos, which, while facing significant hurdles, possessed an undeniable elegance and simplicity that the Ptolemaic system lacked. It was a seed planted in fertile ground, a radical idea that would slowly germinate and eventually blossom into a full-blown scientific revolution. Copernicus himself was not a revolutionary in the modern sense. He still adhered to the principle of uniform circular motion, and his model still required epicycles, though fewer and smaller ones than Ptolemy's, to account for the observed non-circularity of planetary orbits. He was still very much a product of his time, seeking to perfect the ancient Greek ideal rather than entirely abandon it. Yet, by moving the Earth from the center, he opened a Pandora's box of possibilities. He shifted the perspective, literally and figuratively, and in doing so, he initiated a cascade of intellectual inquiry that would eventually dismantle the ancient cosmos and usher in the modern scientific age. The centuries that followed Copernicus would see his ideas taken up, debated, refined, and ultimately proven by a new generation of astronomers and physicists. Tycho Brahe, with his unparalleled observational precision, would provide the data. Johannes Kepler, using Tycho's data, would discover the elliptical nature of planetary orbits, finally abandoning the sacred circle. Galileo Galilei, with his telescope, would provide direct observational evidence that shattered the Aristotelian Ptolemaic worldview. And Isaac Newton, with his universal law of gravitation, would provide the dynamic explanation for why the planets moved as they did, finally uniting terrestrial and celestial physics. But all of this began with Copernicus, with his quiet, persistent intellectual discomfort with the old system, and his audacious leap of imagination. His work was not just a scientific treatise, it was a philosophical declaration, a challenge to millennia of accepted wisdom and intuitive understanding. It forced humanity to reconsider its place in the universe, moving from the static central stage to a dynamic orbiting planet. This was the true beginning of the scientific revolution, a profound shift in how humanity understood itself and its relationship to the vast shifting heavens. The era of early astronomy, defined by observation, myth, and the geocentric ideal, was drawing to a close, and the dawn of modern cosmology was just beginning to break. The seeds of revolution had been sown, and the cosmos would never look the same again.